Good day. You will recall in our last class, we are discussing one example under the product rule, example which is given by the function f of x equal to x cube g of x, for which g of 3 is 3 and g prime of 3 is 1. So here we are asked to find the slope f prime of 3. Okay, so as earlier discussed, we have been able to get that if you want to find the slope of the y-ds of this, we have said this is f prime of x, and this f prime of z will be equal to, according to the product rule, this is the function. We owe this function, okay, why we differentiate this, okay, again, we owe this, why we differentiate this. So when we owe this, this becomes g of x. Then when we differentiate this, this is 3x squared. Okay, so accordingly, so if at x equal to 3, okay, as given here, when x is equal to 3, so we can find the slope f prime of 3, and this will be equal to, wherever we see x, we put 3, and this becomes 3. Okay, as you can see, this is x, so we are putting 3 there. Okay, again 3 here. Okay, and this is 3 multiplied by 3 squared. Okay, so but we have been given that whatever we say the slope of g, okay, at 3, it is 1 here according to this. So if you calculate this, this is 27 into 1 plus, and wherever we see g of 3, okay, this is 3. Okay, so we multiply this. This is 9 times this, that's 27. Okay, and this will be equal to 27 plus, okay, so this g of 3 here is this. So 3 square is 9. So 3 times 9, that's 27. So this is 3. So we can multiply this straight away. Okay, and the multiplication of this is that's 54 27. Okay, this will be 1. So this is 81. Okay, so if you add this together, so this is 108. Okay, so the slope of this function, for which the slope of this function, for which this g of s at 3 is 3, and the slope of g at 3 is 1. Okay, so the slope of f of x when s is equal to 3 is given as this number. Okay, so that's that on the product rule. Okay, so today we want to move on to the quotient rule. Quotient rule. Okay, I will call this part C. Quotient rule. So quotient rule arises when we have functions that are in form of a rational form. That is, if you have two differentiable functions, let's give an example. Okay, let's define this straight away. So if u of x and v of x are differentiable functions, for which y is equal to the rational of this, okay, at this u over v, where u is differentiable and v is differentiable. Okay, so provided that, okay, we must restrict the condition on v, okay, that this v must not be equal to 0. for each x. Okay, so though these two are differentiable with this relationship, but this v must be restricted not to be 0 for each s. For if this v is 0, okay, this function will be undefined. I would not want that. Okay, so if this happens, okay, so the slope of y with respect to x is given by v du dx minus u dv dx over v squared. Okay, so with the decision, as you can see too, the slope also has v as denominator. So okay, so that's why this one will be restricted. So this is what we refer to as quotient rule, and we always use this, as we have said earlier, when we have any function of this form. Though not every time one can use the quotient rule, okay, because there are some functions which do not require quotient rule. For example, if you are given a function of this form, x squared plus 3x, for example, and this is given as over x. Okay, function like this do not require this. Okay, we can simply simplify this so that this is x over x plus 3x over x, and this will be x plus 3. Okay, as you can see, this is a linear function, but this form make it look in a non-well posed form. Okay, so the well posed form of this, when we redefine this, is this. So we can just apply the sum and difference rule to differentiate this. Okay, so let's now see how we get this. So the proof of the quotient rule. So proof, suppose that u of x and v of x are two differentiable functions Okay, so if you say u of x and v of x are two differentiable functions, what we mean is that is the derivative of u with respect to x exists. Okay, that is what we mean when we say u of x is differentiable. Okay, that is, this limit exists, and also the derivative of v with respect to x also exists. Okay, so this is what we mean when we say u of x and v of x are differentiable functions. Okay, it means the derivative and the derivative exists. Okay, so if you have u and v, okay, such that y is the rational form of this. Okay, so we satisfy the condition we posted earlier that this v must not be 0. Okay, so then we want to look at the derivative of y with respect to x. Okay, that is, if this function is given as u over v, so we want to look at this derivative of this function with respect to x, just like what we have here. Okay, so literally this means derivative of u over v dx. Okay, so when we replace this with y, okay, so by definition, this becomes the limit. Okay, as you can see, u over v, that is, this will vary, and the denominator is also vary, minus u of x over v of x, everything over h. Okay, by definition, this is what we have. Okay, and let's take this up so that we can simplify this further. Okay, so we'll not write this. Okay, so let's maintain this dy dx. Okay, since we know that this also means this. So from here, you can find the sum of the two terms in the denominator. Okay, and then we can factor this 1 over h out now to have something like this. Okay, so the LCM of this will be v of x multiplied by v of x plus h. Okay, that's the LCM of these two denominators. Okay, so if we simplify this further, this will be v of x plus h. In this, we have v of x multiplied by this. Okay, okay. The minus here that's coming. Then again, v of x in this will be v of x plus h. Okay, that is, this we cancelled out. Then we're multiplying this with the numerator here, which is u of x. Okay, so that is what we have here too. Okay, so we can move further to introduce a trivial term. Okay, introduce a trivial term here. Okay, so you will recognize the product rule. We also do the same. Okay, we look for the term which are not appear here. Okay, but they are trivial, so we introduce them. Okay, and the trivial term we are going to use here is u of x, v of x. Okay, that's the trivial term we introduce. Okay, negative this, positive this. Okay, as you can see, they are trivial terms, so both of them can cancel out. So minus this term, which is v of x plus h, u of x. Okay, so everything over v of x plus h. Okay, so from here we can now group this term into two. Okay, while we take this one over h in, and when we do that, this becomes the limit. Okay, let us first of all group this numerator before we take this one over h in. So when we do that, this will be, we'll see that v of x is common in these two terms. Okay, so we can factor that out. Okay, so in order to get u of x plus h minus u of x. Okay, again, these two terms, okay, we can factor negative u of x out. Okay, and the reason is to bring this term to the front. Okay, so this will be negative u of x into v of x plus h minus v of x. Okay, so this bigger bracket, let's give this a bigger bracket. Okay, so it's closed there, and everything over v of x plus h. So we are able to group this term into two. Then we can now take this term in. Okay, after which we will now apply the limit to each term, to all the terms in the expression here. Okay, so this will be equal to, so we are taking this term in, so this will be v of x into u of x plus h minus u of x all over h. Okay, we are given this the h because this h is more useful to this term than this. Okay, minus u of x into v of x plus h minus v of x. Also, okay, we are opening a bracket here, so this term also goes for this. Okay, so and this will be over h. Okay, so everything here over this denominator, which is v of x plus h. Okay, so let's take the term up. So the next thing here is to apply the limit to each term of this last expression. Okay, according to the limit law. Okay, the limit of a rational function, when it appears like this, the limit will go for the numerator and the limit will also go for the denominator. Okay, so we are applying about 4 limit law here. The first one is the difference, which is this limit will affect this, and this limit will also affect this. The second one we apply here is the when this limit affects this term, okay, according to the limit law under product, okay, this limit will affect this, and this limit will also affect this. This limit will affect this term, and it will also affect this term, according to the product under the limit law. Okay, again, this limit, when it affects this, it will affect this, and it will affect this. Okay, so that's the next thing we do. We assume the limit law is well understood from our previous videos. Okay, so and that's what we do now. And lastly, we since this v of x is independent of h, okay, we apply the constant law under the limit law, and this u of x is also independent of the letter h. Okay, so we regard this as a constant too with respect to h here, and the same thing for this. So that's the four limit law we apply here. So let's do that one after the other. So this limit, when it goes for this, we have said it will affect this and it will affect this. Then it will be the limit h tends to 0 v of x, the limit h tends to 0 u of x plus h minus u of x over h minus the limit u of x as h tends to 0 multiplied by the limit as h tends to 0 v of x plus h minus v of x over h. Okay, so everything over the limit v of x as h tends to 0 multiplied by the limit h tends to 0 v of x plus h. Okay, so when the limit affects all these terms, this is how it gives us. Okay, so accordingly, this limit will not affect this, as we have said earlier, because this v of x is independent of the variable or the letter h. Okay, but this limit will affect this. Okay, by definition, okay, we have earlier seen this before. So this will be equal to v of x. Accordingly, this means the derivative of u with respect to x. Okay, then minus. This also means this limit will not affect this because it is independent of h. So this is u of x. And what you have here is the derivative of v with respect to x. So this is the v dx. And lastly, at the denominator, this limit will not affect this v, okay, because it is also independent of x, but this limit will affect this because this has an h term there. Okay, this is f of x plus 0. Okay, so wherever we see h equals 0 there. Okay, so accordingly, so when we, for brevity, okay, we write v for v of x, and same thing for this. Okay, so this will be v du dx minus u dv dx, everything over. Okay, so x plus 0 is 0. Okay, so this is v of x, v of x. V of x multiplied by v of x, that will be v of x square. Okay, so let's maintain v. Okay, accordingly to what? V square. Okay, so this is how we obtain the quotient too. Okay, so we have said that this must come with the fact that this denominator must not be 0. Okay, in order to have a defined term for this. Now we now move to examples of some rational function in which we can use the quotient rule. The first example here says we should differentiate the function y equal to exponential x over 1 plus x squared with respect to the argument x. Okay, we have said this earlier that this means with respect to. Okay, so the argument is x here. Okay, so this is why it's depending on x. Okay, so if you look at this function, we'll see that this function is differentiable. That is, the numerator is a differentiable function. Okay, and the denominator is also a quadratic equation, a quadratic function, which is also differentiable for every value of x. Okay, so one thing that will now come to mind is there any x, okay, for which this denominator will become 0? Okay, one could think of any number. Okay, so if this is 0, 1 plus 0, okay. Since x is 0, okay, so there is no such x here that will make this 0. So this means this function is a differentiable function. Okay, so accordingly, this is possible for us to find the slope or the derivative of this function with respect to the argument x. Okay, so we'll say the numerator here is u, and let the denominator also be the 1 plus x squared. Okay, so here I want to apply the formula by the s, which is this will be v du dx over minus u dv dx over dx over v squared. Okay, so from here, the value of v is 1 plus x squared multiplied by d. Okay, u is given by exponential x, so this is exponential x over dx minus, again, u is the exponential x multiplied by d of 1 plus x squared over dx. Okay, so let's bring this here. Okay, so there is no derivative of on this function, so this remains 1 plus x squared. Okay, so the derivative of exponential is exponential. How does this change? Okay, minus exponential x. So the derivative of 1 plus x squared is 2x. Okay, so now for the denominator. Okay, sorry, we do not we haven't had the denominator here, which this is a 1 plus x squared. Okay, so the denominator is this 1 plus x squared, everything squared. Okay, so this is v. Okay, the square of v is this. Okay, so let us simplify this to see whether this term is reducible. Okay, so exponential x is common, so we can bring that out. Okay, and this will be x squared minus 2x. That is, I'm taking this negative for this, then plus 1. Okay, so everything here over 1 plus x squared or squared. Okay, so this is the derivative of this with respect to. So let's see, this can be simplified further. Okay, because this means say, okay, let's drop somewhere here to show the final derivative of this. Okay, we are only trying to reduce this to a smaller term. Okay, so this means exponential x into, okay, the expansion of this is is x minus 1 square. Okay, so when we expand this, we get what we have here. So everything here is 1 plus x square over, okay, 1 plus x square square. Okay, so we are just trying to change this, okay, in the compact form. Okay, so this is the slope of this function. As you can see also, there is no term of x for which this will be 0. There is no term of x which is a real number for which this will be 0. Okay, so this is the slope. Okay, so let's see another example. Okay, but this time let's look at a function under the trigonometric identity. Okay, one of such function is the function y equal to tan x. Okay, with respect to the argument x. Okay, so if we rewrite this tan x, we see that tan x means sine x over cos x. Okay, and accordingly, this is equivalent to the function u, and this is a v. Okay, so but we will recall that this function is differentiable everywhere, as we know. Okay, as we have given in our earlier video, sine is differentiable everywhere. Cos x is also differentiable everywhere. Okay, but there are some point of x, okay, that will make this to be 0. Okay, such function at such point, if x is equal to 90 or pi over 2. Okay, when we substitute this, okay, so this will make this to be this will make this denominator to be 0. Okay, not only this, there are other values that will make that to be 0. Okay, so these are the number 270, or you say 3 pi over 2. Okay, 5 pi over 2, etc. Okay, so we just, what we do is we restrict this. Okay, we restrict this, that is, we are removing all this point. Okay, point of x to be this. Okay, point of x to be this. We are removing them from the point for the slope of this. Okay, so we are removing all these points. We are removing all these points. Okay, 5 pi over 2, etc. Okay, so now we can now find the slope of this. Okay, so since we are given that u is this and v is this, okay, let's go straight to the formula. Okay, so from the formula, okay, we have we have v du dx minus u dv dx all over v squared. Okay, so this will be equal to v, according to this, is cos x, d of u which is sine x, minus again u which is sine x, d of cos x. Excuse me. So this is over cos x all squared. Okay, that is v, which is cos x, so all squared. So if we simplify this further, this is cos x. So the slope of sine x is cos x. We've seen that earlier. And then this is minus sine x. Okay, also the slope of cos x is negative sine x. Okay, as shown in our earlier videos. And this is a cos square x. Okay, so on that tree identity, it's preferable to put a square at the middle. Okay, like this. Okay, so Okay, so let's bring it up so that we can do a very neat job here. Okay, we can remove all this since we have taken note of all this. Okay, so dy dx is now equal to, if you multiply this becomes cos square x. Okay, so this negative become positive. So sine multiplied by sine will be sine square x. Okay, so everything here is over cos square x. Okay, so under the trivial identity, so we note that this term, okay, is 1. So under the trivial identity, okay, so we now replace this term with 1, and also under the trivial identity, we also have that when we have sec s, that's the secant of x is 1 over cos x. Okay, so we apply these two terms here. Okay, so first of all, this is 1 over cos square x. Okay, and this also means 1 over this also means 1 over cos x all square. Okay, since 1 square will give us this by law of indices. Okay, when we see 1 square, so we can factor 1 out here, so by law of indices holds. Okay, so according to this is sec x all square. Okay, so as we have said earlier, it's preferable to put a square at the middle of this. Okay, so what we are saying here is that if we have the function tan x, okay, for which x is not pi over 2, 3 pi over 2, and including negative pi 2, negative pi over 2, negative 3 pi over 2, etc. Okay, so we can have the slope of this, okay, for the same domain. We can have the slope as this. Okay, so that is what we have done here. So lastly, let us consider one more example under the quotient rule. Okay, you will see that most of the example we are considering here are some of the function are quotient function that cannot be reducible. Okay, so in the case when you can reduce the function into a normal polynomial, okay, so one is the quotient rule is not needed in that case. So let us consider one more example. Okay, so one of the example of a quotient function that cannot be reducible into a polynomial function. Okay, so this will be example 3. So we want to differentiate this function y equal to x squared exponential x over x plus exponential x. Okay, so also want to differentiate this with respect to the argument x. Okay, so if we study this function very well, we see that the numerator of this function is a product of two functions. Okay, x squared is a quadratic function. Exponential x is also a is an exponential function. Okay, so we have the product of the two. So what it means is that this product, to find the slope of this product, okay, we need to apply what we call the product rule. So what we have done in our earlier video. Okay, so these are in a separate form, so we use the sum and difference rule for this. Okay, so solution accordingly, we have the numerator here. We select u to be the numerator, which is x squared exponential x, and v is equal to what we have at the denominator. Okay, so also let's now find the slope of this function. Okay, we'll do that separately. Okay, so we'll find the slope of this function also separately. Okay, so at the end, we'll now substitute everything into the formula. Okay, so the slope of this. This time, let's call this the term a term u prime. Let's call this u prime. Let's call this v. Okay, let's call this okay, let's say let's call this term a, and let us also call this term b. Okay, so since the variable dummy, okay, so we can use this to express the formula of a product rule. Accordingly, this will be a db dx plus b dA dx. Okay, so we'll use this to evaluate this term here. So where this a is x squared and this b is exponential x. So when we substitute that, this will be x squared d of exponential x over dx plus b, which is exponential x, d of a, which is x squared over dx. So this will be equal to x squared. So exponential x remain exponential x plus, okay, exponential x into differential of this is 2x. So accordingly, this is x squared exponential x plus 2x exponential x. Okay, so that is the slope of u with respect to x. Okay, again, the slope of v with respect to x is the slope of this is 1. We have said earlier that we apply the sum and difference rule here. So when we differentiate x, it is 1. And when we differentiate exponential, it is exponential x. So we can now substitute this term into the formula. Okay, so don't forget we are in need of this term u, we are in need of this term v, we are in need of this, we are in need of this. Okay, so let's do that quickly here. Okay, so therefore dy dx, which is equal to v du dx minus u dv dx over v square. Okay, so we are retaining this so that we can look at the term to substitute. Okay, so this v is given as x plus exponential x. Okay, d of that's du dx. Okay, we have done that already. Okay, but let's substitute the term so that we'll know the term we are substituting for. Okay, minus u, which is x squared exponential x, d of v, which is x plus exponential x, so over dx. Okay, so let us move this now to have a clearer view of what is happening here. So we have said that is we have said v is this. Okay, so accordingly, this will be x exponential x, and the derivative of this with respect to x is given as this. As we have said that this is x squared exponential x plus 2x exponential x. Okay, minus x squared exponential x into 1 plus exponential x. So everything here is over x plus exponential x all squared. Okay, so we can now simplify this. Okay, now to write this in a compact form. Okay, so if we expand this, this will be x cubed exponential x plus 2x squared exponential x plus x squared exponential 2x. Okay, so we are expanding this term that we have here. Okay, so plus 2x exponential 2x minus x squared exponential x minus x squared exponential 2x. So everything is over x plus exponential x or square. Okay, so let's see some of the terms I can cancel out here. Okay, so if you look at this term will remove one of the term here. Okay, okay, so this remove, and also this also. Okay, this term, so remove this. Okay, so let's use a different pen here. Okay, so this term, remove this. Okay, and also why this term will be reduced by 1. Okay, let's also see. Okay, this one will remain. This one will remain. Okay, so let's see the final form of this. So this is x cube exponential x to x squared. So one time will be reduced here. Okay, because this and these are the same. So this will be plus x squared exponential x. Then we are left with plus 2x exponential 2x. So everything over x plus exponential x or square. Okay. So as you can see, we have said this term has cancelled out. Okay. And then this term, I'll remove one of this term. Okay, so the remaining term is what we have above. Okay. So one can simplify this further to see whether when we expand the denominator, this can further reduce. Okay. Otherwise, okay, we can leave the result as this. Or in the case where we say we should evaluate this term at a certain point of x and y. Okay. So let's give exercises so that whoever is watching this video, okay, at their leisure time can practice the following questions. The first one is okay, so let's say differentiate the following. Okay, the first one is the function y equal to exponential x all over 1 minus exponential x. Okay, so the second one is the function, okay, s equal to the square root of t all over 1 plus square root of t. Okay, here we'll see that the variable t is an independent variable in this case, while the variable s is dependent. Okay, so and thirdly, okay, one can, okay, let's evaluate the slope of this. Okay, at the starting point of this, when t is 1, okay, let's evaluate the slope, and when s is a half. So and lastly 3. So let's find the slope of a function with set s. Okay, so these are the exercises I have for you. Okay, at your leisure time you can practice this. Okay, in the comment section you can put up your question and let's see how we can answer you all the questions. Okay, so thank you. Now next video we'll look at other rules of differentiation.